the small signal is going to be tedious. There will be 2 transistors and 2 resistors. But we're going to solve something very useful called the virtual ground concept. This is very critical. You will see this in the midterm. You must be able to do this, okay? When can we use virtual ground? Let me give you the criteria first. First, you need a differential input. Okay? Only when you're talking about differential input could you use the concept virtual ground I'm going to show earlier. Second, you need to be a small signal. The reason that you have small signal is because we linearize the circuit. Right? Like what you just asked me, the best is the smallest the signal is almost 0. Okay? And third, you need to have an absolute, I will keep emphasize this one, absolutely symmetric circuit. What do I mean? On the left, I have a circuit, very, very simple circuit. And I claim it's absolute symmetric because I draw a line of symmetry. And I need to tell you, you don't know that, I tell you that R1 equals to R2. Is this circuit absolutely symmetric? When R1 equal to R2. It is, right? And I apply a differential input, so this here is a typo. This is negative delta V. Not typo, I means that you go down by delta V. The difference is delta V, but let me put negative to emphasize. The left one, I increase it by delta V, the right one, I reduce by delta V. So that is differential, right? And this is resistor. Of course, it's linear. It's linear circuit, right? Ohm's law. You don't see any quadratic terms. Because of this, I claim that Vx always equal to 0 without solving this circuit. It's absolute symmetric. The input is differential, and it is linearized. Then the center point or those point on the plane of symmetry is always 0. Okay, and let me prove to you. For this case, use KCL. Right? If I call this I1, call this I2, I have I1 plus I2 equals to 0, right? KCL. Now, what is I1? It's delta V minus Vx divided by R1. And I2 is, what is I2 based on the drawing? Is Vx. No, I'm wrong. What should go first based on the drawing? Minus delta V minus Vx divided by R2. Yeah, because this is the direction, right? Need to be very careful. R1 equal R2, they got cancelled. Then what do I get? Delta V minus delta V, cancel. I got 2Vx equal to 0, or negative 2Vx equal to 0. So Vx equal to 0. No matter what your input is for delta V, my Vx is always 0. So if you have circuit like this, you even don't need to solve anything. Draw a plane of symmetry, the middle point is 0. But this does not connect to ground. It's just a virtual ground because the potential is always 0, but it's not connected to ground. Okay? How about a differential pair? Based on what I said earlier, if I draw a plane of symmetry here, and I claim that M1 equals to M2, including the biasing, the conditions are the same, and I have a differential input, right? Same bias. So it is absolutely, again, this is very important. Absolutely, you cannot say it looks like it almost. No, do not do that, okay? So this is absolutely symmetric. Well, it's small signal because this is EE124. Right, this is given. If it is no small signal, then you need to be careful because you cannot linearize the transistor in the way that you want. And it's given differential input. Then what? If I call this, how about call it W? VW equal to 0. Is that a big deal? I discovered VW equal to 0. Even before that, you know it is 0, right? Because it is VDD. We are doing small signal, which is AC ground anyway. But more importantly, VP is 0, right? More importantly, it is that this point is 0. We never know what it is until we solve the whole circuit. But because of these three criteria, I know VP equals to 0. Okay? Again, you can try to prove yourself by proving. I won't, maybe because of time, maybe I'll quickly. We know that IDS1 plus IDS2 must be equal to ISS, right? The total current has to be the same. When I apply the differential circuit, then I know that delta IDS1 plus delta IDS2 must be 0, right? The change. This is the DC. Now I increase this and decrease this, then the difference must be 0. Is that okay? Yeah. So from there, this is just IDS1 plus IDS2 needs to be 0. Okay. And then you follow the GM. IDS1 is just GM times VGS1. And IDS2 is again GM times VGS2. Right? GM got cancelled. VGS1 is what? Delta V minus VP. And VGS2 is negative delta V minus VP. Okay, so as a result, you see VP equals to 0. I need to be fast, go back just like what I did for the transistor, right? Here what I'm doing is, again, small signal. IDS1 equals to GM times VGS1. That's what we have been emphasizing, right? Is this point okay? Transconductance, the role of transconductance. And GM1 equal to GM2 because they're absolutely symmetric. And what is VGS1? Delta V minus VP. VGS2, negative delta V minus VP. And you see that VP equal to 0. So it's virtual ground again. If this is virtual ground, then how should I solve the small signal? This is ground already. Then isn't that this transistor? This circuit is just equivalent to I apply a V here, ground this. Apply a negative V here, ground this. Right? Because this is virtual ground. I don't care about this is open circuit, right? Because I'm doing AC signal. Is this okay? Make sense? Is it surprising or no? Normal, right? Because this is virtual ground. And what is the gain of this guy? Negative GMRD is just a common source. So turn out that it was not a common source pair, but because we are doing differential signal, it's just two pair of common source in AC signal, right? So what is V out and V in? We say V out equals to V, let's say Vy minus Vx. V in equals to V in 1 minus V in 2. Okay? And the gain naturally equals to V out divided by V in, right? But Vy is just equals to GM RD, negative GM RD times negative V. Vy, this is Y. Isn't that it is negative V times GM RD times negative? And then what is Vx? Negative GM RD times V, right? So this is negative GM RD times negative V. And Vx is negative GM RD times V, right? And what is the input? V minus negative V. So the top is positive plus positive. The bottom is 2V. So the gain is GMRD. Right? So it's the same as a common source amplifier. Right? Although you have two pair, but because the input is double, your output is double, but the gain is the same. That is the same as what we expect earlier, what we discussed earlier, right? So we spent a lot of time to talk about this basic thing, virtual ground, whatever. Once we step it firmly, the rest becomes very easy. Because you know very well all this equation, you derive from very rigorous way. That's why the first part is so important. And now I know this is the gain. And let me just, finally, this is the small signal if you want to draw it, right? And how about the power consumption? Let me just quickly see. The power consumption is going to be 2x more, right? But the gain is the same, right? But why do we do this expensive way? Same gain, but different, but more power consumption? Huh? Yes, to reject the noise. Okay, so that's it for today. Thank you.